So here are some examples of past paper questions about polar molecules and intermolecular forces. Which of the following is not an example of a van der Waals force? And this is bold, although it's not shown up quite well. So not a van der Waals force. Van der Waals force is the name for our intermolecular forces, our collective term for intermolecular forces. And the one that is not an intermolecular force is covalent bond. Hydrogen bonding between molecules, London dispersion forces between monatomic atoms and molecules, permanent dipole attractions between polar molecules. Which of the following compounds would be the most water soluble? What they're really asking there is which is the most polar. And if we're looking for molecules that are polar, we are looking for hydroxyl groups, we're looking for NH. So in molecule A, I'm seeing none of that, it's just hydrogens and carbons. Molecule B, I've got one hydroxyl group. C, I've got what we call a carbonyl group there. D, we've got a carbonyl group, hydroxyl group, another hydroxyl group, another hydroxyl group, another hydroxyl group, and a carbon bonded to oxygen there. And the carbon to oxygen, carbon electronegativity 2.5, oxygen is 3.5, so that will definitely be a polar bond there. But even for the hydroxyl groups, you can see this is far more than any other molecule, so D is the most soluble in water, and that's because it's the most polar. The polarity of molecules can be investigated using a charged rod. The charged rod will attract a stream of polar liquid flowing from a burette. And you get a wee diagram showing that there. Which of the following liquids would not be attracted? So which liquid isn't polar? Most of these molecules you'll be familiar with, or should be familiar with. Propanone is a new one you'll meet in Unit 2. We have what we call a carbonyl group here, a carbon double bond O. And we have to look at whether these molecules are polar or not. The easy one to start with is propanol. It has this hydroxyl group. It's definitely polar. Water also has the OH. We know it's polar. The key bit of this propanone molecule is the oxygen-carbon bond here. Electronegativity of oxygen is 3.5, carbon is 2.5, so there will be a charge difference across this bond. Putting our line back in across the molecule, we can see there's also a charge difference across the molecule. The bottom half slightly positive, top half slightly negative, so propanone is also polar. That leaves us with hexane, and it's just carbons, hydrogens. This molecule is not polar. Hexane is not polar, and so a stream of hexane will not be deflected by a charged rod. Which of the following is a polar molecule? The tricky bit of this question is that it's just giving you the formula. It's not giving you the structure, so you're going to have to think about the structures as well. Because remember, if it's a polar molecule, one, there's polar bonds, and then the second part we've got to think about the shape and see is there a charge difference across the whole molecule because of the shape. So we'll take each in turn. We'll start with carbon tetrachloride. Chlorine, electronegativity 3.0, carbon is 2.5. Chlorine will be slightly negative compared to the carbon, which will be slightly positive. Using our line, is there one bit of the molecule that's different from another? No, negative this side, negative this side. Turn our line round a little bit and see there's still no difference, still negative this side, negative this side. And you can be doing this with a pen, pencil, ruler, just moving it through the molecule. Is one part of the molecule different from the other? carbon tetrachloride, there's not a different charge at one side from the other, so it is not polar. Next up is ammonia, nitrogen, electronegativity of 3.0, hydrogen 2.2. So nitrogen will be slightly negative compared to hydrogen, slightly positive. And we bring our line down, we can see one half of the molecule slightly negative, the lower half slightly positive. There is a charge difference across this molecule. So ammonia is a polar molecule. We'll look at the other two just for completeness, but B is going to be our correct answer. Carbon dioxide, oxygen has an electronegativity of 3.5, carbon is 2.5, so these bonds are polar. Is there a charge difference across the molecule? No, there's not. One side is not different from the other. Carbon dioxide is not polar. Finally, methane, hydrogen, we have an electronegativity of 2.2, carbon is 2.5. The bonds are very, very slightly polar. But when we bring our line in to split across the molecule and see if there's a charge difference at one side of the molecule compared to the other, we see there is no difference at all. So methane is also non-polar. So as I said, B is the answer. Ammonia is the only one that's polar. But it wasn't enough just to look at the bonds. We had to look at the shape of the molecule as well. The structure of caryophyllene, which can be extracted from clove oil, is this. Which of the following would be the best solvent for extracting caryophyllene? Well, looking at this structure, all we've got is carbon and hydrogens. This is a hydrocarbon. There's no polarity here. There's not the key groups that we are looking for, the hydroxyl groups or the NH. That's our telltale signs, or even your C double bond O, sometimes telltale signs. These two are most important for a polar molecule. The molecule is non-polar. We need a non-polar solvent for this molecule. Non-polar solvents dissolve non-polar molecules. So having a look at the structures down below, this one's no good. This you'll find in Unit 2 is shortened structure for this here. We've got a polar carbon double bond O bond there. This is the same feature, double bond O. Looking at D, if we look closely, we'll see there's a hydroxyl group there. D is also polar, which means our answer is A. And again, looking carefully at A, we'll see this is a hydrocarbon. The molecule is not polar. Chloramines are less soluble in water than ammonia due to the polarities of the molecules, and so readily escape into the atmosphere, causing irritation to the eyes. Explain the difference in polarities of ammonia and trichloramine molecules. So there's 2 marks for this question, which means there's 2 bits of info needed. They've asked us to explain the difference in polarities of these 2 molecules. So that's where to start. Are they both polar? Is one more polar than the other? We need to look at the polarity of the bonds first and then think about the shape of the molecule. So we've looked up our electronegativity values, and that's going to allow us to assign dipoles across the bond if there are any. So hydrogen, nitrogen, you can see there is a difference in electronegativity there. We will have polar bonds. Trichloramine is nitrogen with chlorine. We've got the same electronegativity there. These bonds will be pure covalent. There'll be no difference in attraction of the electrons. The electrons will be equally shared. So no polar bond, no polar molecule. So in putting together your answer, you don't need to write an essay. You need to get the key points across. Ammonia is polar. Popping our line in there, we can see that there's a charge difference across the molecule. So we're putting down our electronegativity values, we're saying the bonds are polar, and we're saying the molecule is polar due to shape. For the trichloramine, it's non-polar. We've got our electronegativity values. We're saying bonds are not polar. The molecule is not polar. Now, how are the marks divvied up here? This statement here about one being polar, one being not polar, that's your first mark. This bit here, where you're doing your electronegativity values, you're talking about polar or not polar due to shape, due to bond polarity, that's where you get mark 2. So we have an open question here. The viscosity of alcohols depends on a number of factors: strength of intermolecular forces, the size of the molecule, temperature. These factors can be investigated using alcohols and apparatus from the list below. Using your knowledge of chemistry, identify the alcohols and apparatus that you would select and describe how they could be used to investigate one or more of the factors affecting the viscosity of alcohols. Viscosity is how easily a liquid flows, and we've been looking at intermolecular forces, so we're going to take a look at this question in terms of the intermolecular force, strength of intermolecular forces. We should know by now that if we have polar groups, like the hydroxyl group that we'll get in alcohols, we've got a polar molecule. And the more hydroxyl groups there are, the more polar it will be. So we're going to have a look at the different alcohols here and see if we can see ones where we're increasing the number of hydroxyl groups, so increasing the polarity. There's loads of different things you could look at in this question, but I'm just going to look at one angle of it just now. So I've selected propan 1-ol, propan 1,3-diol, propan 1,2,3-triol. I'll give you structures of these in a second. But that's me looking at the number of hydroxyl groups, tri being 3, so there's going to be 3 hydroxyl groups here, 2 hydroxyl groups here, 1 hydroxyl group here. But we could have been looking at other intermolecular forces. You might have said, okay, I'm going to just keep 1 hydroxyl group and we'll see, as the size of the molecule increases, maybe we'll focus on London dispersion forces instead of what I'm looking at here, hydrogen bonding between the molecules. Maybe pause the video just now and see if you can think of any other combinations that you could look at, looking at, is it London dispersion forces? Is it going to be hydrogen bonding? Are you looking at the size of the molecules and how the intermolecular forces vary with that? What other combos could we have? So these are the molecules we're working with: propan 1-ol, hydroxyl group, first carbon, propan 1,3-diol, propan 1,2,3-triol. Now you'll meet these molecules properly when you get to Unit 2. So here we're increasing the number of hydroxyl groups, so we're increasing the polarity, the strength of intermolecular forces, the strength of the hydrogen bonding between molecules will increase as we go across. Now we haven't even got to the point of talking about the experiment here, but already we've got structures. We can add in this wee bit of information here that the strength of hydrogen bonds between molecules increases due to more hydroxyl groups. Already you're shown a knowledge of chemistry before we've even got to the experiment. So this would be worth marks in itself. So maybe you're just having a blank and you can't figure it out. Put down something, anything at all. Some structures, more hydroxyl groups mean more polarity, and this leads to an increase in viscosity. So maybe that's all you can put down, but put it down because you'll get marks for that. So one way we could look at viscosity, or a measure of viscosity, is to get some glass tubes. We're going to get some stoppers and a timer. And we've got our alcohols already. We're also getting a little ball bearing. So we get the tube ready. We take a stopper out, fill up the tube with the first alcohol, pop a ball bearing in, stick the stopper in the top. You would then upturn the tube and time how long it takes for the ball bearing to drop, and you would repeat this a few times to get an average value. You can then change the liquid and put your next alcohol in and repeat the experiment doing the same. Another method would be to fill a burette with the chosen alcohol and open the tap and time how long it takes to empty a set volume of the alcohol from the burette and repeat that several times over. It's always good to round off these answers by saying what you would expect to happen. So you would expect that as we move towards the propan 123 trial, it would take longer for the ball bearing to drop down the tube, because you would expect this to be more viscous because of the stronger hydrogen bonds between the molecules. The table below shows the boiling points and structures of some isomers with molecular formula C6H12O2. We've got various structures there. Name the intermolecular force which accounts for the high boiling points of isomers 1, 2 and 3. Comparing the boiling points, these ones are quite low compared to these ones here. What's the big difference? This is a kind of spot the difference type of question. We've got double bond O and a bond to O here. We've got that over here as well. Lots of carbon and hydrogen, lots of carbon and hydrogen. But what is different about these three that these others don't have? And it's the hydroxyl groups. So the hydroxyl groups are going to allow for hydrogen bonding between molecules. So your answer for this would be hydrogen bonding. Thiols are compounds that contain an SH functional group. They often have very strong, unpleasant odours. Now, you're not supposed to know about thiols. They're not in the higher course. This is partly problem solving and partly knowledge and understanding. They're trying to get you to apply your knowledge in a new situation. Ethane thiol is used to add a smell to gaseous fuels in order to give warnings of gas leaks. And we've got our structure there. A student used the boiling points of ethane thiol and propan 1-ol to compare the strength of intermolecular forces. A. State the reason why propan 1-ol was a suitable alcohol to compare with ethane thiol. When we're doing any comparison, we need it to be a fair test. And what we need to remember here is that all molecules are going to have London dispersion forces between the molecules. If we've got polar molecules, there's also going to be either permanent dipole interactions or hydrogen bonding between molecules too. Now these are stronger than the London dispersion forces. All van der Waals forces are weaker than metallic, covalent, ionic bonds, but we have varying strengths within the van der Waals forces. London dispersion forces are weakest, but all molecules will have London dispersion forces between them as an intermolecular force. So if we want to do a comparison of permanent dipole or hydrogen bonding forces between molecules to see if they're there or not or how strong they are, we need to rule out our London dispersion forces first and make sure it's a fair test. How do we do that? Well, the strength of London dispersion forces depends on the number of electrons. More electrons, stronger London dispersion forces. So for a fair test, we need the same number of electrons in each molecule. So be 6 electrons for each carbon. We will have 16 for the sulfur and 1 for each of the hydrogens. So total electrons here will be 34 electrons. Doing the same with propan 1-ol, adding up all the electrons from propan 1-ol, we get the same 34 electrons. So these are good to compare because they have the same number of electrons. Any difference in the intermolecular forces will not be down to a difference in the London dispersion forces. It will have to be due to something else. B. Explain why propan 1-ol has a higher boiling point than ethane thiol. Your answers should include the names of the intermolecular forces broken when each liquid boils. To know which forces are broken, we need to think about, are these molecules polar or non-polar? We'll start by looking at the electronegativity values for the different elements in these molecules. So looking at these electronegativity values, between carbon and hydrogen, only a difference of 0.3, very slightly polar, not much. Carbon and sulfur, there is no difference in electronegativity, so these are all pure covalent bonds here. And then again, hydrogen, sulfur, very slight difference in polarity there. So you could argue that this molecule was non-polar or perhaps very, very slightly polar, because in reality this bond is actually bent here, and so we will have a slight charge difference across the molecule. With propan-1-ol, we've got this hydroxyl group, and as soon as we see hydroxyl groups, we know that there's hydrogen bonding between molecules. Back to this question and how we're going to phrase our answer. Explain why propan-1-ol has a higher boiling point than ethanethiol. Your answer should include the names of the intermolecular forces broken when each liquid boils. So your first mark is for identifying that there's permanent dipole interactions between ethanethiol molecules, and there's hydrogen bonding between propan-1-ol molecules. Now SQA did accept the London dispersion forces between ethanethiol molecules here as well. Your second mark is for recognising that it's these intermolecular forces that break when these chemicals boil. So it takes more energy to break the hydrogen bonding between propan-1-ol molecules, so there's a higher boiling point there. Tin-4 iodide is a compound formed from a metal and a non-metal element. Tin-4 iodide is a bright orange powder that dissolves easily in non-polar solvents. It has a melting point of 143 degrees Celsius and a boiling point of 340 degrees Celsius. Name the type of bonding and structure present in tin-4 iodide. Okay, this first bit, metal and non-metal element, that's there to distract you. Ignore it. What we have to focus on is the properties, and it's listed some interesting properties. It's a powder that easily dissolves in non-polar solvents. Ionic compounds dissolve in polar solvents, not non-polar solvents. So if you're thinking metal and non-metal, it's ionic, well, here's our first clue that it isn't. It dissolves in non-polar solvents. Second, it has a melting point of 143 degrees Celsius and a boiling point of 340 degrees Celsius. That's low. Ionic compounds tend to have melting boiling points above 1,000 degrees. There's a few exceptions to that, but most of them are well above 1,000 degrees. This isn't. So we've got a low melting and boiling point. It dissolves in non-polar solvents. That's telling me it's covalent, and it's covalent molecular based on the melting and boiling point. Covalent is the bonding, molecule or molecular be the structure. So two different parts here, make sure you get them both. Covalent for the bonding, molecule for the structure. So it's now time for you to try some questions yourself. Have a go at the questions that we've put on the form. There are explanations for the longer answer ones there, but if you need any further explanation, you can just click the box saying you need more explanation in the live webinar. And remember, if there's any feedback you want to give us about how to improve, please put that in the form as well.